the disclosure. So I'm a scientific advisor for Chiron Medical Technology and also Definions. And as a disclaimer, I'm a computer scientist, so not clinical expertise per se, but hopefully I can convince you that the methods we are working on are trying to support you as radiologists in your task. So I want to focus on one specific task, which is image segmentation. So we have seen wonderful examples in the previous talks where AI or machine learning can be applied, but here I want to focus on one task that I believe is important. It's something we can do on radiology images, and it's something that radiologists hate to do. So it's segmentation of structures. So here's an example of an MRI scan with multiple sequences, and the task is to segment that MRI into different parts of anatomical structures or pathological structures here, where we have a brain tumor, glioblastoma. And we would like to identify for each point in the image whether it belongs to the active part of the tumor, the necrotic part, the edema, or the healthy part. So this allows us to do quantitative assessment. It allows us to take measurements on images, and it is a very important task to do. The problem is it's a quite challenging task. So if you just look at 5 different examples of patient data, you know that tumors can have very variable shapes. They can appear almost anywhere in the brain. Of course, there are some preferred locations, but there's a lot of variability. And of course, everything happens here in 3D over multiple images. So if you ask a radiologist to do this manually, they would prefer not to do it. However, it has been shown that it's actually a quite useful thing to do. In particular, for instance, if you do clinical trials where you want to see whether a drug works or not, we know that, for instance, just taking simple measures like RECIST, maximum diameter, and so on, do miss certain changes. For instance, you would like to know whether a tumor changes its active parts into necrotic core, and so on. So we have seen a lot of progress in using machine learning methods for doing these type of tasks, and over the past couple of years, everything has moved towards deep learning. Why is that the case? If you look at the deep learning system, and we have seen some very nice introduction and examples already of a neural network, the goal here is to build a system that has many, many layers. And these layers basically allow you to extract information from the images, and initial layers, first layers, do very simple feature extractions from images, and later layers build up on those features. So the power of deep learning compared to previous machine learning techniques is that you start to learn features of features of features of features. And this allows you to abstract, to get very good abstractions of your data that eventually allows you to do predictions, like classifying whether there's a dog or a cat in an image, or whether it's a tumor or not. So Curtis had made a nice case of saying where this comes from. So it has really started in computer vision. People like Fei-Fei Li, who created these ImageNet databases, were some of the pioneers who made those systems possible for detecting whether there's a human or a cat or a dog in an image. And that was based on databases that had millions of images. So we just heard ImageNet contains 14 million images. That's usually not the data we can access in medical scenarios. So we need to adapt these architectures. So this convolutional neural net that I'm showing here, which we call DeepMedic, was developed a couple of years ago in our lab, which was specific to medical data. So first of all, it could take in 3D volumetric data. At that time, there wasn't much around, so you couldn't just download a library that did this. But it also takes multi-sequence data, so basically 4D data if you want. And then it has a specific architecture where, in this case, we use 2 pathways. One is processing the image at its highest resolution, so you see all the fine details, which you do need to make the final decision of whether something is abnormal or not. But also at the same time, it processes the image at a lower resolution scale, which gives you context. Because very often, for instance, in brain lesions, you do not only want to make a decision based on a very localized feature, but it depends where you are in the brain. If you think about traumatic brain injuries, for instance, they usually tend to happen at the front of the brain because maybe you had a car accident. So learning the context, knowing where you are in the image and where you are spatially located is important for these systems. So you need to think about certain types of architectures that do allow you to capture that information. So here are just some examples. So we tested this system on traumatic brain injuries, as I said, actually with the Addenbrooke's Hospital in Cambridge, one of our clinical collaborators, where we looked at just 61 patients. So you might think that doesn't sound a lot in terms of training data, but if you think about this actually being 4D data and you extract many different examples of positives and negatives from those 61 4D MRI scans, you do get actually millions of training points. So we could show that this works reasonably well. So the important thing here to note is that the system is able to not only detect larger regions, which are easy to spot and delineate manually, but also like very fine and small details at the same time. And that's really important. In particular in TBI, you often have microbleeds, which are, as I learned, very important prognostic markers about patient outcome and recovery. So when we did the quantitative analysis, what was interesting is that this system does perform compared to a human quite well. So these are DICE scores for lesions. If you're above 60, you're okay. You're not that bad. Actually, an important measure is volume of lesions. So lesion load is an important prognostic marker. What we found is there are two cases where we were completely off in terms of predicting the volume of lesions. Once we over-predicted and once we completely under-predicted. Interestingly, when we went back to our clinical experts, looked at those subjects, the manual annotations were wrong. So we used this as a computer scientist, whether I do TBI or brain tumors, it's not much of a difference, to be honest. I get input data and I want to delineate something, so we applied this to stroke. That worked reasonably well. Again, we could detect small and large lesions at the same time with this network. And we won this challenge. So the interesting thing is there are a lot of challenges out there where you have publicly available data, where you can train your systems, and then you evaluate your systems on test data that you run it and then you send it in and they do the evaluation so that you actually can't cheat. So this system that we developed, DeepMedic, was performing quite well back then already. What was interesting for us as well is to actually look at how the machine does it. So think about, we give it a brain scan and a lesion map saying, where is the lesion, how do you segment it? The system itself now needs to start figuring out what are the features in the image. And you can visualize them. So here we are showing what are the patterns that are learned. And what's interesting is that some of those patterns are interpretable as humans, so you can look at them. For instance, we did find that the high resolution pathway was learning to segment out certain structures like the ventricles or the white matter, which does make sense to some degree, because if you want to find a lesion, it matters whether you sit in the white matter, gray matter, and so on. The lower path was doing what we expected. It basically learned location. So it learned whether you are in the back of the brain or at the top part. So now this is interesting that those features are learned automatically. So you only give it an image and a lesion map, and the network does seem to do something sensible. Not all of those feature maps are interpretable. Unfortunately, 95% of them, if you look at them, you have no idea what they mean. So you can use, as we heard earlier, these networks for many, many different tasks. It's a very versatile tool. So we use it for cardiac imaging, where this time we do have a large data set. I mean, in our context, large, 5,000 subjects almost, where we trained on 4,000 of them to automatically segment the heart in cardiac MRI. And this is manually annotated data. It's coming from the UK Biobank imaging study. Anyone can access that. And we could show that the system, again, does do very well in terms of automatically segmenting those images. More importantly, it does it very efficiently. So segmenting a 4D cardiac MRI can be done in just a few seconds. More importantly than showing that you get nice images with nice segmentations, we compared how well does it do to human experts. So in this case, we had 3 experts doing the whole manual annotation on a small subset, 50 cases. And what's interesting here to note is that if we compare the variability between humans, it's in the same range as the variability that we find between the automated segmentation and the best possible manual segmentation, which is estimated by doing some consensus over the experts. So that's quite promising, and an indication for us at least that we seem to be at the level of human experts automatically. So you can apply this to other domains. Of course, mammography has been mentioned earlier. It's a domain where a lot of things are happening, and we see deep learning systems coming up. So if you want to learn more about this, I recommend this extra session on Saturday run by Kiron Medical. So you find that in room Z on Saturday. We apply this to whole body imaging. Many of you might know that whole body imaging is uprising. I saw there was a session this morning talking about whether it's the right time for doing whole body imaging. My feeling is that radiologists are not super happy about that. So at least in the UK, the NICE guidelines have now been updated that whole body imaging is the imaging method to use in things like myeloma and lymphoma, where you need to assess the whole body, whether you have metastasis. Unfortunately, those scans come with lots of slices you need to look at, and obviously doing the visual manual inspections of all those slices will just add to your time that you need to spend in front of the screen. So we are trying to develop a system that does automatic analysis of those whole body images. So first of all, we start to look at the major organs, so we can automatically segment the main organs in the scan, which is kind of nice because it gives us a bit of a roadmap. Like a GPS system that we can use when we now afterwards analyze individual slices. We roughly know where we are and what are the next neighboring organs to make further decisions. And this works reasonably well with the systems that I described earlier. So in particular for the larger organs, heart, lung, liver, kidney, we do get very, very good performance. So again, this is die-score. It's kind of an overlap measure done between manual and automatic segmentation. And you get very good scores there for the bigger organs. However, there are organs which are very difficult to do currently automatically, like pancreas or the clavicle bones here in this case. Smaller organs, smaller structures, and variable structures, which currently those neural networks have still difficulties with. Here are just some visual examples, all done automatically on our cohort of whole body scans. So now, of course, if you can do that, you can think about extracting phenotypes. If you, again, think about the UK Biobank study, which collects actually whole body imaging, Dixon sequence to do like whole body fat measurements and things like this. If you can automatically segment all the organs, you can start correlating that with things like demographics, lifestyle, genetics, and so on. But we are interested in lesion detection, so we want to help the radiologists in doing the screening and doing the detection on those scans. So we extend the system to do lesion detection on diffusion, weighted MRI. Here are just very preliminary results, so this is work in progress, where we try to automatically detect lymph nodes. And you see the manual and the automatic one, excuse me, are not that different. So the big challenge is robustness with these methods. So currently, we do see a lot of performance drop when the input data changes. That's a huge challenge. I discussed this a little bit in an earlier session over lunch. And we need to think about how to avoid performance drops when the input data changes. But also, different models have different weaknesses. And currently, as a computer scientist, I'm faced with this agony of choice. If you give me your data, nicely curated, of course, and well manually annotated, I still have the problem of designing the system and making choices that have nothing to do with the actual clinical applications. So I need to make choices on how to train a system, what the system looks like, what are data sampling strategies, and so on. And all these decisions are made by me as an ML expert, and I might do the wrong decisions, and that might influence the performance of the system. So how do I make the best decision here? So we came up with a model that we call EMMA, ensembles of multiple models and architectures, where we basically say, we can't make that decision. So why don't we train lots of different methods and take old machine learning theory of ensembling outputs from different methods to increase robustness. And that works really well. And the hope is that inconsistent mistakes can be averaged out. So we applied this again to brain tumor segmentation, and I'm showing you a couple of examples, visual examples of what the system does and what the human expert does, and you can tell me which one is which. So this is one result, and I'm flipping forth and back a couple of times just to make sure that you do see the difference. Here's another example. And And another one, and maybe one more. So who believes this is the manual one? And who believes this one is the manual one? There's not much difference, right? The first one is the automated one. Actually, the automated one and this one always looks a little bit smoother, because the way the human expert has to do it is slice by slice, and you find a little bit of discontinuities between slices, which the machine doesn't do. Okay, so that led us to another nice picture in front of a projector. So we won this challenge, the Mikhail Bratz challenge, which is the brain tumor segmentation challenge. One of the biggest challenges, again, not that many subjects, but we have about 300 patients to train and test on. So now the big question is, how do we go beyond human level performance? So hopefully I could convince you that deep learning methods can achieve human level performance on some tasks. Cardiac imaging, breast cancer, brain tumors are maybe among them. The question is, what are the limiting factors for going beyond? Obviously, it's the input. So we train on manually segmented data, so we can only be as good as this. So it's important to know this limitation, and it's also important to have the right expectations on machine learning methods. What you feed in is what you can replicate. If you want to go beyond that, you need to think about what to feed in. One way could be to synthesize data, to actually synthetically generate training data. Another way could be to change what you're optimizing for. Is it really the segmentation that you're interested in, or is it the downstream task of predicting outcome of your patients? And maybe you want to incorporate that in the machine learning training. So I invited, in my earlier talk today, I invited all clinical people to actually join us in building these machine learning methods, and I try to argue for systems that should be co-designed by clinical experts and machine learning experts. So we do see human level performance. You could argue that in some cases we do already see superhuman level performance, because obviously if we are on par on accuracy, we are still much faster with the machine. But I want to emphasize that we're not trying to aim to replace anyone here. We're trying to do a task that you hate to do anyhow, but that would be useful to do, to further do your analysis. So we need to think about how to turn, for instance, segmentation tools into clinically useful tools. I think currently we're still at a state where it's not clear how that actually impacts your workflow and how it at the end improves patient care. So we need to understand the current limitations, and we need to think about robustness. If you give me a training data set from your hospital, let's say in Germany from Essen, I'm pretty sure it will not work on a cohort that is on a different continent in a different hospital. So we should definitely not ignore domain knowledge. So we need to bring everyone on board. We need to have teams that consist of clinical experts, machine learning experts, computer scientists. They need to solve all these challenges together. That's the team. I in particular want to highlight those 4 people on the right, because they are the clinical people who do the tedious stuff of annotating the data that we need to train our machine learning methods. Thank you very much.